So now we are going to problem number 3. The problem says that let R be the relation on Z. Z means set of all integers defined by R equals to AB such that A comma B belong to Z and mod A minus B less or equal to 5. Check whether R is reflexive, comma, symmetric and transitive. So clearly mod of A minus A equal to 0 and that 0 is less or equal to 5 for all A belong to Z. That means if we take any A belong to Z, any element from the set of all integers, A, B, C, any. So like A minus A, that is equal to 0. Or we can choose B minus B, that is equal to 0. So that 0 is less or equal to 5. That means this A or B, this A that is A minus B. So this this A and this B are equal, so we have A minus A, that is equal to 0, and that 0 is less or equal to 5, and this inequation holds for any integer A belong to Z. So it is clear that by the definition of R, okay, if mod of A minus B less or equal to 5, then AB belong to R. So here we see that mod of A minus A equal to 0 and that 0 is less or equal to 5. That means mod of A minus A less or equal to 5. This holds. So A comma A, this A comma A belong to R, and this holds for all A belong to Z. So and this is the definition of reflexive relation. So clearly R is reflexive. Reflexive on Z. You can write. So on Z, that is vital. The R is reflexive on Z. So now for the second part, symmetric part. So let AB belongs to R, where A and B should belongs to Z. Because of the definition of R is here, AB belong to Z. That's fine. So AB belong to R. By the definition of R, it is clear that mod A minus B less or equal to 5. So since AB belongs to R, so mod of A minus B less or equal to 5. Okay. This can be written as like that, mod of minus of B minus A, and that is less or equal to 5. So minus that minus is common. So mod of minus B minus A. Sure. So that mod of minus A, the logic is mod of minus A equal to mod A. So we can add mod of minus B minus A, that is equals to mod of B minus A, and that is less or equal to 5. And by the definition of the relation R, here mod of A minus B less or equal to 5, so AB belongs to R. Here mod of B minus A less or equal to 5, so B comma A belongs to R. And this happens, so R is clearly symmetric on Z. It is clear absolutely. So our second part is done. Now our third part. Third part is what? Check it that the relation is transitive or not. So how to check it? If we consider, take A equal to 1, B equal to 4, C equals to 8. So what happened then? Mod of 1 minus 4 equal how much? Mod of minus 3, that is equal to 3, and that is less or equal to 5. Obviously 3 is less or equal to 5. This inequation is true. So which is true? So clearly mod of 1 minus 5 less or equal to 5, and by the definition of the relation R, so 1 comma 4 belongs to R by the definition of R. So similarly, if we take mod of 4 minus 8, that is equal to mod of minus 4, that is equal to 4, and 4 is less or equal to 5, which is true. So 4 comma 8 belongs to R. But so look at that, 1 comma 4 belong to R and 4 comma 8 belong to R. That 4 and that 4 are equal. So if the relation is transitive, we can show that 1 comma 8 belongs to R. Oh, but mod of 1 minus 8, that is equals to mod of minus 7, that is equal to 7, that cannot be less or equal to 5. So 1 comma 8 doesn't belongs to R. So 1 comma 8 doesn't belongs to R means what? R is not transitive. And the problem is done. Clear? Very good. So we are going to the next problem. Problem number 4. The problem number 4 says that let A equal to 1, 2, 3 be a set, non-empty set obviously. Define a relation on A which is reflexive and transitive but not symmetric on A. And number 2, reflexive and symmetric but not transitive on A. Let us consider or define a relation R1 on A as follows. R1 equal to 1 1 2 2 3 3 2 1. Clear? We can show that this relation is reflexive, transitive, but not symmetric. How? So look at the mother set is what? Mother set is A equal to 1 2 3. So for the, if this relation R1 is reflexive, then 1 1 2 2 3 3 must be there. Yes, it is there. 1 1 is there, 2 2 is there, 3 3 is there. Then by the definition of reflexive relation, R1 is reflexive. Clear? Now transitive portion. Transitive portion. So what happened then? So look at that. 2 2 belongs to R1 and 2 1 belongs to R1. Clear? What is the common portion? That 2 and that 2. Clear? The common portion is like that. Common portion is this 2 and that 2. Clear? Then 2 comma 1 must be R1. Yes, 2 comma 1 must be R1. So this relation is transitive. Similarly, we can see that. Look at that. 2 1 belongs to R1. 1 1 belongs to R1. What is the common portion? This one and that one. Clear? So 2 comma 1, that 2 and that 1 should belongs to R1. Yes, 2 comma 1 belongs to R1. So this relation is clearly transitive. But this relation is not symmetric. How? Look at that. 2 1 belongs to R, but the opposite of 2 1 is how much? 1 2. 1 2 doesn't belongs to R. So R1 is not symmetric. Clear? Again repeated that. Clearly we see that A comma A belongs to R1 for all A belong to A. That means 1 1 belongs to A. Sorry, R1. 2 2 belongs to R1. 3 3 belongs to R1. So clearly R is reflexive on A. You can write like that. Okay. Again, AB belongs to R1 and BC belongs to R1. So AC belongs to R1 holds. Clear? But the same logic. So clearly R1 is transitive. But the last part is, but we see that 2 1 is belongs to R1, but 1 2 doesn't belongs to R1. So R1 is not symmetric. So first part is done, and second part is left to the students. Okay. So you can do that. Do the sum. Find the relation R1. It is your homework. Okay. Do it. Very good. So now we are going to the next problem number 5. A relation R is defined on N as follows. R equal to xy such that xy belongs to N and 2x plus y equal to 41. Show that R is neither reflexive nor symmetric and transitive. Clear? Now, for the solution of the problem, we have to consider x equal to 2 and y equal to 2 in that equation. That equation. What happened then? So 2 into 2 plus 2 how much? 4 plus 2 how much? 6 not equal to 41. So this equation cannot be satisfied. So 2 comma 2 doesn't belongs to R. Similarly, we can show that for x equal to 1, y equal to 1, how much it is? 2 into 1 plus 1, how much? 3. 3 not equal to 41. So 1 comma 1 doesn't belongs to R. Similarly, we can show that 1 comma 1 doesn't belongs to R. So R is not reflexive. Clear? So now for the symmetric part, clear that 2 into 1 plus 39 equal to 41. So what happened then? Instead of that x, how much it is? 1, this one. Instead of that y, how much it is? 39. So what happened? 1 comma 39 belong to R according to the definition of the relation R. Clear? So 1 comma 39 belongs to R. But we see that if we take instead of that x 39 and instead of that y 1, what happened? 2 into 39 plus 1, how much? 78 plus 1, that is 79, not equal to 41. So which does not belongs to R? 39 comma 1. Instead of x is how much? This x is how much? 39 and this y equal to 1. So 39 comma 1 doesn't belongs to R. Here we see that 1 comma 39 belong to R, but 39 comma 1 doesn't belongs to R. So R is not symmetric. Clear? Very good. So now for the next part. 20 comma 1 belong to R. Yes, Obviously, because 2 into 20 plus 1, how much? 40 plus 1 equal to 41 belongs to, so to a 20 comma 1 belongs to R. Again 1 comma 39, obvious, what happened? 2 into 1 plus 39 equal to 2 plus 39 equal to 41, so 1 comma 39 also belongs to R. So what is the common portion? This one, and that one are the common portion. So if this relation is transitive, then 20 comma 39 should belongs to R. But we see that 2 into 20 plus 39, how much it is? 40 plus 39, how much it is? 79, not equal to 41. So 20 comma 39 doesn't belongs to R. So R is not transitive. Clear to everybody? Thank you.